Good morning, everybody. Can you guys hear me okay?
Yes.
Okay, awesome. Um, so we're going to finish up this week's new material with chapter 4 today. Let me pop up the PowerPoint slide somewhere here. There we go. Okay, so there is already a video in D2L for the for section 4.5. And so my goal today, I mean, if we have extra time, but I don't think we will, my goal today is to make sure that we get through 4.1 through 4.4, and then 4.5 there's already a video for. So that should help a little bit today. Maybe we can get it in a little bit shorter time frame. On Tuesday we were almost at 3 hours, so hopefully we can get through it in the couple hours that we have, or at least a little bit over that. Does anybody have any questions on that? And you guys know that the Zoom meetings, we're not going to have those after this week, right?
Unfortunately.
Yeah, I'm sorry. Now, but what I want to tell you guys is don't hesitate to contact me, and I can do like a Zoom office hours with anybody if you need. I'm just not going to do these because I have the recordings already, but that actually opens me up a little bit, you know. So if anybody has questions, you want to, you know, meet and do a few problems together as if we were in my office during office hours, I would be happy to do that. And I can do it if anybody's watching this recorded later. I can do it at a different time besides Tuesday and Thursday morning. It doesn't have to be Tuesday and Thursday morning. So we can find a time that we can both meet. I'm pretty flexible. So keep that in mind. And the other ones, although you can't pop in and ask a question, it's the same format that we've been doing. So it's just a recorded version of this. So, okay. Let's look at the 4 things that we're going to count or talk about today. So this section or this chapter is very different from what we've been doing, and it's very different from what we're going to do after chapter 4 and 5. So chapter 4 is on probability. Now, statistics and probability are often taught together, but they're different branches of mathematics. So it's like saying trigonometry and algebra are the same thing. They're not the same thing. A lot of times trigonometry is taught in a college algebra class, but they're different branches of mathematics. So probability deals with the likelihood of something happening, or the different ways things can happen, but it's not exactly statistics. Even though we often teach them together. So for chapter 4 and chapter 5, we're going to be talking about probability. And then when we get to chapter 6, we're going to be back to strictly statistics and stick with strictly statistics for the rest of the semester. So I have seen, I've seen a lot of students who like probability better than statistics, or vice versa. It's kind of like that preference between some people like geometry better than algebra, vice versa. In fact, I've seen a little bit of correlation between, it seems that a lot of people that are more like geometry type people tend to kind of like the probability. It's kind of a visual thing in my mind more than algebra is. And statistics, you know, statistics and algebra are kind of more, you know, follow these rules, get the answer. Whereas geometry and probability are a little bit more fluid. But anyway, just so you know, it's kind of a little bit different thing. One thing that frustrates students is that different problems can be the same type of problem, but look a little different. It's hard to learn how to categorize things. So the biggest thing with that is just practice. So, and also me trying to be real clear about what I'm going to expect and all of that. So before we stop my ramblings, and we'll get going on the material. So probability itself can be defined as the chance of an event occurring. We can use probability in 2 ways. We can talk about odds, and we can also talk about We could talk about odds, and we could talk about strictly the chance of it happening. So odds is a little bit different. We don't really do much with odds in this book. Let me show you the difference. So if I'm looking at a six-sided die, you know, it's got your six sides. I don't know why I drew that one the other way, but anyway. So you've got your die with its six sides, and you want to know what's the probability of rolling a 3, let's say. The probability of rolling a 3 would be 1 out of the six sides. So we'd say the probability is 1/6. But on a lot of things that you see, one that comes to mind specifically, lottery tickets, they'll list the odds. The odds is a ratio between what you're looking at and what you're not looking at. So for the odds for this, they would say the odds are 1 to 5, because this is what you want and this is what you don't want. So if we're looking at the odds of a 3, we would say 1 to 5, because there's 1 that's what we want, and then there's 5 that are what we don't want. So they're just slightly different. We don't really do odds much. What we do in this book, and what's really more common, is this probability idea. So you would say 1 out of the 6. Some examples of how we see probability in every day is weather forecasting. It's how they set insurance rates. They say, well, you fall in this category. You have this job, you have this credit rating, you have this many prior accidents, you're this gender, you live in this town. They use all these different criteria, some which, you know, seem a little unfair, but they take all of those things into account, and then they set what they want to charge you based on what they think they may have to pay out for the average person in your category. So anyway, that's where it's used. Now there are, by the way, if that interests you, that job category is called actuary science, being somebody who predicts like how much a company should charge for things based on the probability and all that. That's called actuary science, and it's actually pays quite well. So a probability experiment is a chance process that leads to well-defined results called outcomes. So a probability experiment could be something as simple as rolling a die. That would be a probability experiment. I pick up the die and I roll it and I see what comes up. I experiment with what the probability of it is. Then we have the outcome. The outcome is the result of a single trial of the probability experiment. So let me clarify this, by the way. A probability experiment doesn't have to be just what I just mentioned. Would be a single trial. So let's clarify this. It doesn't have to just be rolling a die once. It could be rolling a die a certain number of times. So we could roll the die 100 times, and that would still be your probability experiment. Okay. And then the outcome is the result of a single trial. So if you rolled the die and the first time you got a 3, you know, that would be your outcome of your first trial. And I'm not going to ask you necessarily like to define these on a test or anything like that. I guess I could possibly ask it as a multiple choice kind of thing. I would say if I'm going to ask something about these, it would be sample space. You really should know, you know, the definition of a sample space. But we're going to do a lot of sample spaces, so hopefully that'll stick. And then a sample space is all the possible outcomes. And so for a die, the possible outcomes are 1, 2, 3, 4, 5, or 6. So the experiment is rolling it 100 times. The outcome is what happens on each roll. So you would write down your outcomes while you were doing your experiment, and then your sample space is what can happen on each roll. So each roll you could either get a 1, 2, 3, 4, 5, or 6. And then an event is all the outcomes. So I'm going to say all the outcomes recorded. I mean, you don't have to record them, but that's what you would typically do if you were doing a probability experiment. You would write them down, and so when you were done, you would have your event. So 3 is your outcome of your first roll, and then when you write down 3, 5, 7, 2, 1, 1, 3, and you write all of those down 100 times, that would be your event when you were done with it. It's like the raw data. It's like the collected data. Does anybody have any questions on any of those? The biggest thing is just when you're doing your homework, if you get confused about what they're asking for, you could look back and see. Other than that, like I said, if I was going to ask you to define something or you know, multiple choice of something, it would be sample space probably. Okay. So the next thing that we're going to look at is some sample spaces. So I'm going to try to put this up here without the answers so that we can fill them in. Sorry, I'd like to set this up a little bit before we get started with class, but this morning got away from me a little bit. Okay, so here's our some examples or some experiments, and we're gonna look at what are the sample spaces for these experiments. So if we were doing an experiment where our experiment was to toss a coin a certain number of times, what would be the sample space? And sample space, remember, means the possible outcomes. So what are the possible outcomes of tossing a typical coin?
Heads or tails?
Heads or tails. So that's our sample space. And usually we abbreviate it. So you would say like heads, tails, something like that. But that's all we mean by sample space, just what could happen on each trial. When you roll a die, we already did that one. That's 1, 2, 3, 4, 5, or 6. Now that's a single die. If we put 2 die, then you know that makes it a much bigger sample space. Answer a true false question. Well, the only outcomes are true or false. And then tossing 2 coins, that has a little bit different. That's a little bit different than just tossing 1 coin. When you toss 2 coins, you could get a head on the first one and a head on the second one. What are some other options?
Heads and tails.
Heads and tails. Okay. What other ones?
Tails and heads.
Tails and heads, and then
Tails and tails.
tails, tails. Now here's a question. Is heads, tails, and tails, heads actually different?
Yes.
Yes, they are different. So these are different. I mean, typically, you could define your experiment differently where you're just going to say, I'm going to count the number of heads. And so, you know, this would be 2 heads, these would both be 1 head, and this would be no heads. So they could be considered the same. But typically, we think of these as different. We think of, you know, coin 1 coming up heads and coin 2 coming up tails as different than tails, heads. As far as the probability of it, there's 4 possible outcomes, and that's really important. Even if we define these as the same, that would make this twice as likely to happen. So you'd have like a 1 in 4 chance of getting heads, or getting 2 heads, a 1 in 4 chance of getting getting no heads, and a 2 in 4 chance of getting a single head. So it still matters even if we try to redefine how we're counting it. Let me do another one really quickly. Let's start the sample space for 2 dice rather. We're not going to write this all out because it gets kind of big. But if we were going to roll 2 dice, and we think about it with the heads, tails, we could, of course, have 1, 1. We could have 1, 2. We could have 1, 3. 1, 4, and so on. 1, 5, 1, 6. So that's all the different things that could happen if the first one comes up a 1. But then we would have to list out, okay, what if the first one comes out a 2? Well, you could have a 2 with a 1, a 2 with a 2, a 2 with a 3, etc. And then you'd have to have this all the way down. So this would go all the way down to 6, 1, and all the way up to 6, 6. So how many different ways, just 2 dice that only have 6 sides on them, how many different possible outcomes do you get? If I wrote
36.
36, there's a lot of different ways for you to roll 2 dice. And again, we're not talking about the total. We can talk about the total, you know, so we could think of, you know, well, how many ways are there to get a 2? How many ways are there to get a 3? And so on. But overall, there's 36 different ways, and that's going to be important in our probability. I want to pull something up really quick, and I want to mention this to you. If you guys are doing something with your homework, do not hesitate to pull something up on Google. It is perfectly fine, and I actually encourage you. They're asking you something about dice. Simply type in sample space 2 dice. You'll get all kinds of results, and then it'll give you a picture of it. So I would look at like images, and there you go. You have all kinds of different versions. You know, this one's kind of a more pictorial thing where you've got the pictures of the dice. Hold on, why is that not opening? There it is. So where you've got the pictures of the dice, or this one, it just lists it out with the numbers like we were doing. But don't hesitate to do this. You're not quote unquote cheating by pulling one of these up for something big like this. The other one that we're going to be talking about a lot, and this one I would definitely say pull it up while you're doing your homework, especially if you're not a card player. They do a lot of deck of cards kind of problems. And so pull up, you know, you could do the one that actually has the pictures. I kind of like this one. It just has the names and the pictures, so it's not quite as busy as this one with all the cards. But the, you know, pull this up while you're doing your homework. If I was to give you one on a test, I would give you the sample space for cards. I don't expect anybody to magically become a card player just because they took a, you know, 1 chapter of statistics or probability. So on the test, if I ask you something about a deck of cards, I'll give you the sample space. So there's absolutely no reason you shouldn't, you know, use it on your homework. Just in general, though, since we are going to use it a lot, you guys can see this okay, right? You guys are seeing the pictures okay? Okay, good. Just in general, I'll go away. When you're looking at a deck of cards, some people aren't quite, again, some people have played cards a lot in their lifetimes. Some people haven't. So let me get my... So when you're looking at these, ace is typically replaces the 1. Sometimes in some games the ace is high, but in our book they usually just think of the ace as a 1. And then these cards up here, these are what are known as the face cards. They're the ones that literally when you have a card would have a face on it. It'd have the picture of the jack or the queen or the king. So they call these face cards. So if it asks, you know, what's the probability of face cards or something, that's 12 cards. The other thing, you know, they could say red or black. Of course, these are the red cards. These are the black cards. This is hearts. Nobody has a problem with that. This is diamonds. Nobody has a problem with that. But these people get mixed up. It really doesn't matter that much if you get them mixed up. But just for clarification, this is spades and these are clubs. If you have a hard time remembering that, look at what they're shaped like. This actually looks like a little garden spade, if you think about it, like a little handle, and you could dig in the garden with it. Looks like a little shovel. So this looks like a little garden spade. And this, this comes from, I know you're like, how does that look like a club? This looks like a medieval club, like with a handle with the 3 things on the end that you could bonk somebody over the head with. That's where that name comes from. It's supposed to be like a little medieval club. At least that's what I found when I looked it up. That's why it's called a club. So this is called a spade because it kind of looks like a shovel, and this is called a club because it looks like a medieval club with the three things on the end that you'd bonk somebody on the head with. So anyway, don't hesitate to pull these up while you're doing your homework. It's not cheating by any stretch of the imagination. Okay, so let's look at the next thing. I think the next thing, oh, they actually have a sample space, but I wanted to just show that you could find it on the internet if you needed to. So here's the book had a slide of the sample space of rolling die, 2 dice. Another thing I wanted to point out on the sample space for the dice is if they are asking you probabilities about totals, I want you to note that the totals are in the columns. So there's one way to get a 2. There's 2 ways to get a total of 3. There's 3 ways to get a total of 4. There's 4 ways to get a total of 5. So see how those are in the diagonals? That'll help you find them a little bit easier. So if on a problem it asks you, you know, what's the probability of rolling a 7? Well, there's 1, 2, 3, 4, 5, 6 different ways. So you'd say 6 out of the 36 ways. But they're always in the diagonals like that. Anybody have any questions on that before I clear this out? Okay. So and I'm going to say that, you know, a lot of these problems, they're really oversimplified. So don't take anything, sometimes they are a little politically incorrect. So just try to not take, you know, just don't take that to heart. Just do what the problem says. So for gender, we're going to talk about children has 3 children. And we're just going to say boy, girl, for the possibilities. So what are the different possibilities if you have 3 children? How do you build this? Well, the first thing that you would do is you would start with probably one of the all categories. So all boys or all girls. So we'll start with boy, boy, boy. And then remember that, you know, where that letter is makes a difference. We're going to try to figure out like all the different ways to have 1 girl and 2 boys. So typically what I do is I start, and they did it here too, is I will start with that new letter at the end. So I'll say boy, boy, girl. You could do girl, boy, boy, it doesn't matter. So this would be like the first child is a boy, second child is a boy, third child's a girl. And then I take that letter, that single letter, and start to shift it. So it could be on the end, it could be in the middle, or it could be at the front. And that's the only things that could happen. The girl could either be the last child, the middle child, or the first child, but that's all the ways that you could have 2 boys and a single girl. Is everybody okay with that? With that kind of that shifting of that letter?
Yes.
Okay. That way when you're trying to list them out, you don't miss something. You want to kind of try to follow some sort of pattern so you don't miss one of them. Okay, so now the next thing is, what if you had 2 girls? So if you had 2 girls and a single boy, again, you could think of the boy as being the last child and then just shift where that boy is. So girl, boy, girl, boy, girl, girl. And you're thinking of that last letter or that single letter, that B, is shifting from the last spot to the middle spot to the first spot, and then the other 2 are the girls. And then lastly, of course, what do we have for our final option?
All girls.
All girls. And that's it. We know we've got all the different ways because these are all the ways you could have 1 girl. These are all the ways you could have 1 boy. And then you could have all boys, all girls. And we know we've got all 8 of them. So this is the sample space for 3 children in a family. And there's 8 possibilities. And again, you can look at it differently, and we will in a bit. You could say For instance, what's the likelihood of having one girl? Well, there's 3 ways that you can get that out of 8, but it's not 1 out of 4, it's 3 out of 8. That's completely different as far as the probability. Okay, so they have this. I don't like this way, but some people do. This hurts my brain. But if you have a hard time keeping track of things, you can do a tree diagram. And how this goes, like I said, though, this hurts my brain, is you start with your first 2 possibilities. So boy, girl, you know, the possibilities for a single trial. And then you branch that off and you say, okay, once I have a boy, after that I could have another boy or I could have a girl. So it could be boy, boy, or boy, girl. And then off of each of these, you branch the 2 possibilities, boy, girl, boy, girl. So what this branch means is you could have boy, 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 that's this one, boy, boy, girl, that's this one, and you can list it out like that. Boy, girl, boy, boy, girl, girl, and so on. So if you like that better, feel free to use it. I tend to use, not tend to, I always do it this way. The tree diagram hurts my brain. Does anybody have any questions on that at all?
The tree diagram isn't going to be like a question on the exam or something. It's just an option to
Just a,
sort
yeah.
your data.
Yeah, it's just it's an option to try to get all the different things in the sample space without missing something. So
Okay.
only use if you want to, you need to. I mean, there may be a question in the homework where it asks you to do a tree diagram. I don't think there is though. There might be, but it wouldn't be anything on a test. So, okay, so the next thing we're going to talk about is the different types of probability. Now, they here in the notes just talk about one at a time, but I'm going to go ahead and define all 3 of them right away just because I think it's easier to keep track of them if you hear all of them at once instead of trying to keep them all separated. So there's 3 types of basic probability. We're going to talk about classical probability first, that's why it's blue, and then we're going to talk about empirical, and then we're going to talk a little bit about subjective. But what are these? Well, classical probability is what we were just doing. It's where you look at dice, we'll say dice, coins, cards, drawing a name out of a hat or a number out of a hat, anything like that, where you're actually like looking at an object or a group of objects and you're saying, oh, well, there's 6 sides on that dice and I could roll, you know, I could roll a 3, that's one of the sides, so it's 1 out of 6. So this is usually very object based. So like usually you have a physical object, usually. Empirical probability, when you do it, it doesn't really feel much different than doing classical probability as far as the work that you do. But empirical probability, we use information from a study or experiment. So it would be like, you went out and you know, took a survey or watched people as they walk by and you said, it looks to me like, you know, 30% of the population has brown hair. 20% of the population has blonde hair. Another 30% of the population has black hair. Another 10% of the population has gray hair. So when you take that from that study and you say, okay, 30% have brown hair, and then somebody says to you, what's the likelihood if I pick a random person from the population that they have brown hair, you'd say 30%. But that information is from the study, it's not from some physical object. So this is a little less perfect because you've got, it's from a study, and studies and samples and stuff are never perfect, but we still treat it very much when we do it in practice like this. But this is called empirical. I'm not sure why it's called empirical. I'm not sure where that name comes from. But this classical, if you can just remember classical and subjective, those are the two that are easy to explain why they're called that, and then empirical is the other one. So classical is because it's the classical objects that we think of with probability, dice and coins and cards and all that. Empirical is when we do a study, and then subjective, that definitely, the reason they use that word, remember when we have like a subjective opinion, that means like it's kind of up to you a little bit. It's kind of up to your experiences and what you think. Well, what kind of probability would be left up to people's opinions or what they think? Can you guys think of anything? Where they call it a probability, but it's very, very much based on what a person, how a person interprets it.
Favorite color?
Favorite color would probably actually be empirical, because you'd probably do a study on it. And yeah, that's a person's opinion. But here, I'm saying the actual probability is actually somebody's opinion based on the data that they have. That's not a hard, solid study experiment. Let me throw one out here. Weather.
I was going to say the temperature.
Yep, the predicted temperature, like not what it is this minute, but what it's going to be this afternoon. You know, the chances that it's going to be, 90 degrees today. Or the chances, the one that we hear all the time is it going to rain, or is it going to snow, or is it going to, is it going to be windy? Those types of things. But probability with weather is usually something about the precipitation. What's another one that would be very subjective, but you hear it stated as a probability? Just think of another one. There's two big ones that we hear all the time. The other one is sports. I mean, there's a whole market based on that. All the gambling on sports is based on subjective probabilities. What is the chances that this team's going to win versus that team? And that's very subjective. You can't be perfect, any given day. Somebody, some team could win even though they have a really low possibility of winning based on the data. But these are very subjective. A person, looks at these and they could, they just have to kind of make a guess based on what they know. And one person could say the probability of this team is winning is 1 in 3, and another person could say the probability is 1 in 4, and they'd both be right because it's subjective. Whereas these, there's only one right answer. So these, there could be more than one right answer based on somebody's opinion. So we don't talk a lot about subjective probability because we want stuff we can actually just calculate. But make sure you know the difference between these three. So like I said, classical, just remember that's what we think of with those physical objects. Subjective is, it's subject to somebody's opinion. And then empirical is the other one, the study or the experiment. Anybody have any questions on that? Okay. So we're going to start, like I said, with classical. And in classical probability, we're going to use the sample spaces, and I've kind of alluded to this or said this a few times already. It uses the sample spaces to determine the numerical probability that an event will happen, assuming all the outcomes are equally likely. So like we have to assume that getting a heads or a tails is equally likely, that rolling a 4 is equally as likely as rolling a 1 or a 2 or a 3 or a 5 or a 6. So we're not talking about, loaded dice. They used to, years ago, there used to be a lot of stuff like that. There's not as much anymore because it's harder to get away with, but people used to make loaded dice where one side of the dice was heavier than the other. You couldn't really feel it when you just held it in your hand, but it had something in it that made one side heavier, so it would roll a certain way. Same thing with coins. They would do things with coins to make it so one side flipped more often than the other. But we're talking about just things that aren't like that, that are just where you flip a coin, you got equal chance of getting heads and tails. And some notation here, P of E just means the probability of something happening. So like if I said the probability of rolling a 3, that's how we would write it. So P3 means probability. Oh, there goes my pen again. So probability of a 3. That's what that means. And then the N of E means like the number of desired outcomes. So in this case, there's 1 3 on the die, and there's 6 total. So that's all that means. Number of events, number of possible outcomes. So 1 out of the 6 is what I want. So there's 1 3 on the dice, and there's 6 numbers on the dice. So we say there's a 1/6 chance of that happening. So that's all this means. Any questions on that one? Okay. So I don't think this is in your slides. This is one of those rounding rules again. So when we're doing probability, the rounding rule is that you should always do it as a reduced fraction. So if it, if we were doing one like with the dice, with the die, and I was looking like what's the chances that you're going to get an odd on the die, that would be 3 out of the 6 sides are odd, 1, 3, and 5. I wouldn't leave it 3, 6. I would reduce that to 1/2. You can use it as 3, 6 while you're working it, but as your final answer, you should, reduce the fraction. The other thing you could do is you could round it to 2 or 3 decimal places. 3 is more common in our book. So if something didn't come out perfectly, say on your calculator, when you calculated the probability, it came out to be 0.76539118, and more digits after that. Typically what we would do is we'd round it to 3 decimal spots. So you'd say that's approximately 0.765. And then in contrast, let's say this wasn't a 3, let's say this was a 7. Then we would say this was approximately 0.766 because we would round it up. So we're rounding that after it's a 7, so we'd say it's about 0.766. And so usually it's 3 decimal spots. And the reason for that is if we wanted to change it to a decimal or to a percentage, that's about 76.6%. So it takes the percentage to like 1 decimal spot. But you don't have to worry a whole lot about that because in Connect Math, it'll tell you where to round it. When you're doing the test, a lot of it is multiple choice, so they're already rounded for you, so you don't have to worry about that. And I wouldn't on the test, I wouldn't give a problem where I would just switch an answer to did you round it right or did you not round it right. It'll be 4 completely, different answers. There wouldn't be 76.5 and 76.6 as answers. So it'll be rounded for you most of the time and everything. So you just mostly have to worry about that in the homework and just follow what it says. Okay. So now it's going to ask if a family has 3 children. I'm just going to write this down rather than put the slide up. It says if a family has 3 children, find the probability that exactly 2 of the 3 are girls. Okay, so that's what it's asking us to do. So I'm going to jot down our sample space again. Remember our sample space was this. Okay, so that was our sample space, and it wants to know what's the probability that 2 of the 3 girls, or 2 of the 3 children are girls. And you'll be surprised what I'll see for an answer for this is 2/3. People just look at that and they say, oh, well, it's 2 out of 3. 2 out of 3 is 2/3. Nope, that's not what we mean. We want to know how many of these options are 2 girls. So which options am I looking at?
The column on the right.
Okay, except for, would I count this one?
GGG.
Yeah. Would I count the GGG?
Mm,
No.
no.
No, because of the way it's worded. It says 2 of the 3 are girls. It doesn't say at least 2 are girls. So it could say that. It could say what's the probability that at least 2 girls. We'll do that one after this one. But this one says 2 out of the 3 are girls. That's what the question asks. If a family has 3 children, find the probability that exactly 2 of the 3 children are girls. So this doesn't have 2 of the 3 children girls. It has 3 of the 3 children girls. So we wouldn't count that one. So from our definition, we're supposed to find how many ways what we're looking at can happen. So that can happen 3 different ways. And then what's our total? What's our bottom number?
8.
8. So it's not 3/4. We're not looking at just these ones. It's not 2/3. You have to look at the whole sample space and count how many are what you want. So in this case, 3 are what I want out of a sample space of 8. This one would be 4 out of 8 because we would include this one. So this one, you would include the last one. If they said at least 2 girls, then you could include the 3 girls, which would be 4 out of 8. And then, of course, you'd reduce that to 1/2. All right. Let's look at the probability rules. I'm going to pop these up all at the same time because they're very related. So there's one of them. This is probability rule number 2. Oh, what happened to my other one? Hold on a second. Okay. Sorry, my computer is not cooperating with me, or I'm being an idiot, one or the other. Okay, hold on. Copy that. There's rule number 1. Here's rule number 2. Rule number 3. And rule number 4. Okay, so the first probability rule says that the probability of any event E, event E just means, like in our example, the probability of getting a 3, probability of having exactly 2 girls. That's just whatever you're looking at. Is a number that you can put as either a fraction or a decimal. We just said how to do that to reduce it or take it to 3 spots. But it has to be between and including 0 to 1. So a probability can only be between 0 to 1. Let me take that one step further. Think of it as a percent. So 0 is 0%. The probability of the event occurring has to be somewhere between 0% and what's 1 as a percentage?
Is that like 100%?
100%, exactly. So the probability has to be somewhere between 0% and 100%. So it could be, 0.572, but it cannot be 5.72. That's impossible. That's like 572%. Can't have that. So when you're getting your answers, they have to start with a 0 something, or be 1. It could be 1, but that's the limit. Somewhere between 0 to 1, and that's it. Okay, so the sum of all the probabilities in the sample space is 1. So think of the die. The probability that we would roll a 1 is 1/6. The probability that we would roll a 2 is 1/6. The probability that we would roll a 3 is 1/6. If I keep doing that, probability of a 5, probability of a 6. If I add those all up, what is that total? Well, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 is 6/6, which is 1. So if you take all the things that can happen and you add them all up, you're going to get 1. because it's 100% chance you're going to get one of those things. So what this is kind of saying, I'm saying what's the probability that you get a 1, 2, 3, 4, 5, or 6? Well, that's 100% chance, which is 1. So that always, all the possible things have to total up to 1. And then this, to me, these next two is almost just kind of reiterating what we already said. If you have something that absolutely cannot happen, the probability of that is 0. So we'll start with something that's sensible. What if somebody said, what's the probability of rolling an 8 on a regular die? You know, a regular 6-sided die, what's the probability of rolling an 8?
0.
0.
0.
0. You could do it with 2 dice, but if you just have 1 die and it's got 6 regular sides, 1, 2, 3, 4, 5, 6, there's no chance out of those 6 sides that you're going to roll an 8. So the probability is 0. And we could even get, you know, a little goofier with it. So if you're, you know, if you've got a 6-sided die, what's the probability that you're going to roll an A? Well, there's no letters on that die. So no way out of the 6 sides that you're going to roll an A. You know, what's the probability when you draw from a deck of cards that you're going to draw, you know, the suit pumpkin? Well, there is no suit pumpkin, so it'd be 0. But it could be also just that it's been removed. So let's say, you know, you say in a deck of cards, you've removed all the reds. Well, then the probability of getting a red is 0 because you've removed all the reds. So anytime that something absolutely cannot occur, the probability is going to be 0. And then on the other hand, if the event is absolutely certain to happen, it's going to have a probability of 1. So like this, what's the probability that you're going to roll a 1, 2, 3, 4, 5, or 6? So what's the probability on a regular die that you're going to roll from 1 to 6?
100%.
100%. And it should say here inclusive. So you could get a 1 or a 6. So that's 6 out of the 6 sides are 1 to 6. So you have a 1 chance. What's the probability when you draw from a deck of regular cards that you're going to get red or black? Well, every single card is either red or black out of the 52. So it's a 52 out of 52 chance. Since we're talking about does anybody have any questions on these? I want to say something really quick about the cards while we're on the cards. Okay, so since we're talking about the cards, mention a few things. When you are looking at the decks, remember we had I think I still have it pulled up here. Let me see if I do. Yes, I do. Okay, so when you're looking at this deck of cards, when you're looking at the different, why won't it, hold on, I can't get it to give me my writing tool. Come on, Zoom, cooperate. That's weird. It won't give me my writing tool from Zoom. Okay, so let me do a snip really quick. We can get around. Oh, there it goes. Now it's decided to do it. Okay, so when you're looking at this, of the suits, there's 4 suits. And so for each of the suits, since there's 32 total, there's 13 because it goes 1 to 10 and then Jack, Queen, King. So there's 13 of each suit. Okay. There's 52 total. If you're talking about reds and blacks, there's 23 red, or 26 rather. There's 26 red, 26 black. We already talked about that in each suit there's 3 face cards, so total there's 12 face cards. Just some kind of things to note. It'll help you a little bit with your homework. So there's 12 face cards. And it seems like there's something else I was going to say, but I can't remember. So that's kind of the big ones, that there's 13 in each suit, which means, and then there's half red, half black, 12 face cards. I think that's it. If there's anything else, you can kind of look at it as you do your homework, but I just wanted to point those things out. Okay, so let's look at some of these. These are just things to kind of emphasize what we just talked about with the rules. Okay, so it says when a single die is rolled, what's the probability of getting a number that's less than 7? We really basically already did this. A number less than 7 would be 1, 2, 3, 4, 5, or 6 on a die. So 6 out of the 6 sides, which is 1. And then let's do one with cards. So if you had a deck of cards, what's the probability that you're going to draw a card that's a 15? Well, that's not possible. None of the cards are 15. So 0 out of the 52 cards, that's 0. So here's a example of the 1. Absolutely has to happen, must happen, cannot happen. So, okay, so I have to take a break for 1 second. I'm getting a phone call, so I apologize. Sorry, don't know what that was. Okay, hold on. I'll be right back. Okay, sorry guys. So next we're going to look at what are called complements. Complements are based on that idea that everything added up has to total up to 1. So if you think of complements as just being the two different things that could happen, then together those two have to add up to 1. So for instance, if I'm looking at a die, if I say the probability of rolling a 3, like we were doing before, and then we look at the complement of it, which is the probability of not rolling a 3, these two together should total 1. So the probability of rolling a 3 is 1 out of 6. And then the probability of not rolling a 3 are the other 5 out of 6 sides. So we have a total together, these have to total 1, because that's everything that can happen, a 6 or not, or a 3 or not a 3. And these are called complements of each other because they're like the opposites of each other, kind of. Does anybody have any questions on that? Okay. And when we do the complement, one way to say it's the complement is to put a bar over it. They really don't do that this very often, but if we wanted to, we could say the probability of not 3. Like you could write it like that, but they really don't do that very often. It's usually only if you just have the E that they put that bar over it. So because these have to total 1, the other thing that you can do with this is if you know one of the complements, you can find the other complement by subtracting it from 1. So if I say I don't know, in a deck of cards, the probability of getting a face card is 12 out of 52. What's the probability of not a face card? Well, you could either count all the not face cards, or you could say 1 minus 12 out of 52, or 52 out of 52 minus 12 out of 52. That leaves, there were 52 cards, we took out the 12 face cards, there's 40 that are not face cards. So this is what it's saying, is if you know one, you should be able to find the other by just subtracting. So we take the 52 minus the 12, and that leaves 40 cards out of the 52 that are not face. And of course, we'd reduce these. Neither one of these are reduced. 6 out of 26, which is 3 out of 13. Actually, I should have done that before I did the not face cards, because that would have been easier. So this is 10 out of 13. Because 3 13ths and 10 13ths total up to the 1. So I should have done the reduction. It would have made the problem easier. Okay, so now they're just going to ask us, or just going to show us a few complements. You know, here's the regular event. What would be the complement of it? So rolling a die and getting a 4, the complement of that would be getting a 1, 2, 3, 5, or 6, or you could even say not getting a 4. Selecting a letter of the alphabet, getting a vowel. You know, so that would be A, E, I, O, U. Then the complement of that would be getting a consonant, and they would have to define what, if Y is a vowel or a consonant. So in this case, it says assume Y is a consonant, then the complement would be getting a consonant. Selecting a month and getting a month that begins with the letter J, well, that would, the complement of that would be getting any month that didn't start with a J. Day of the week and getting a weekday, the complement would be getting selecting a day of the week and getting a weekend, Saturday or Sunday. So everybody good with what a complement is? Okay, that's usually something that is pretty clear. Okay, so now this one, they kind of cheated a little bit, because on this next problem, they actually are doing, well, let me put it up here and then I'll say what. So we've been doing classical probability on all these problems. Is this problem right here, classical probability? It says in a study, it was found 23% of the people surveyed said vanilla was their favorite flavor. If a person selected at random, find the probability that the person's favorite flavor of ice cream is not vanilla. So
Isn't that empirical?
yeah, that's empirical. So they kind of cheated here. They kind of got ahead of themselves, because the next slide talks about empirical. So I guess they could say they were trying to lead into it. But the probability of vanilla, they tell us, is 23% from an empirical study. So the probability of not vanilla, well, that must be everybody else in the study. If they only let them pick one flavor, if 23% said vanilla, then that means the other 77% said not vanilla. Because we take out the 23% that said vanilla, that leaves the other 77% in the study. And yes, this is definitely empirical, not classical, if they were to ask you that question. Okay, so all the other ones we were doing were classical, but this is empirical because it's from a study. Okay, so that's the next thing that they have here. They have the same slide. We already did this slide. Just have the slide of that. There's classical, empirical, subjective. Classical's the when you have a fixed, a solid object to look at. Empirical's from a study or a survey, and then subjective is like the weather and sports. So now, like I said, you kind of have, you really basically do almost the same thing with empirical that you do with classical, as far as when you're working one of the problems. It doesn't feel like it's that much different, but you just look at the study and you see how many in the study, or what percentage in the study had what you desired, and you divide it by the sum of everything. It's technically a little bit different than we do with classical, but it really doesn't feel much different when you're doing it. So we're going to go back and look at this one that we had from with the blood types. If you guys remember from chapter 2, it says if you have a sample of 50 people, 21 had type O, 22 had type A, 5 had B, 2 had AB. What's the probability that a person has, it's right here, it's kind of snuck, it kind of snuck it in here. What's the probability that they have type O? Well, out of this study, how many people had type O? 21. And how many total? 50. So it's not that much different than if we had, 50 chips in a bowl and we were going to pick out a random one, and the chips were marked with this. So it's kind of like you have 50 chips in a bowl, 22 of the chips say A, 22 of the chips, or 5 of the chips say B, 2 of the chips say AB, and 21 say O. Then the chances that I pick out a chip that says O on it is 21 out of 50. I mean, it's slightly different because you're talking from this study and instead of, a bowl of chips, a bowl of objects. But when you do it, it doesn't really feel that much different. Is everybody okay with that one? Good.
Yeah.
Good. Okay. Now I'm going to not put up the slides. I'm just going to put up the questions for these next ones. So what's the probability that you have A or B? Well, if we're looking at A or B, we have to look at anybody that's in either of those categories. So we're going to look at this one and this one. And there's 2 different ways you can write it. The book writes it like this. It writes 22 out of 50 plus 5 out of 50. I actually kind of like to think of it as add them and then put it over 50. So I know again, it's subtle, but I think this is probably what most people do, is they think of it as 22 plus 5 out of 50 rather than 2 separate probabilities. They think of, let's add these together first and then take it out of 50. So anyway, the final answer is 27 out of 50. Okay, and then the next one, are you guys okay with the or? So if it's or, it doesn't mean they have to be both. It just means we're going to count if it's in either category. So far? Okay. Yep. Okay, so the next one says, what's the probability that a person has neither, so we're kind of doing a complement here a little bit, neither A nor O. So you could look at the A's and the O's and then subtract out, or you could look at just the ones that aren't A's or O's. So try to get rid of this without erasing the numbers. Didn't do a very good job. Okay, just remember that was a 22 that I just erased. Okay, so neither A nor O means we're going to count the, which ones? Can't count A's. I can't count O's. So I'm going to count these 2 only. So 7 out of the 50 are neither A nor O. And then this last one is really a complement question because it says, what's the probability that someone has, do I have room here? Yeah, I do. Okay, so what's the probability that someone does not have AB? So not AB. I mean, we could go up here and we could say, okay, not AB is 22 plus 5 plus 21 out of 50. But I would venture to guess that what people would do is they would just say, oh, well, 2 have AB. So why don't I just do 50 minus 2 out of 50? Rather than doing 22 plus 5 plus 21, you're going to say, oh, well, 2 have AB. I don't want to count those, so there's 48 left over. I mean, you get the same thing, but this is where that complement comes in handy, is if you know it's easier to subtract it off than to add up all the others, go ahead and do it. It's quicker and easier. Any questions on any of that stuff? Okay, so we're going to move on to the last thing, and all it has on this last thing is it just says a really quick blip about subjective probability. So it just says subjective probability uses a probability value based on an educated guess or an estimate, has to employ opinions, inexact information, and that's weather forecasting and sporting events are the big ones. There's other ones, but those are the biggies. Okay, so that's it for 4.1. So we're going to get into 4.2 here, and 4.2 is on, that's not the right one, is on the addition rules. So when we're talking about addition rules in probability, one of the things that we really have to understand is, or know what it means first, is what is mutually exclusive. Because it matters when we're looking at something if the events are mutually exclusive or not. And what mutually exclusive means is that they don't overlap. So mutually exclusive is when you can't be both at the same time. So for instance, and we'll have some examples here in a little bit, but just a real quick for instance. For instance, if you're looking at a die, you couldn't roll a 2 and an odd at the same time, because 2 and odd are mutually exclusive from each other. There's no 2s that are odds. There's no odds that are 2s. So those would be mutually exclusive from each other. Something that's not mutually exclusive, being a healthcare major and being a sophomore. Well, you could be a sophomore healthcare major, so those are not mutually exclusive from each other because they can happen at the same time. And the reason that we do this is because if it's mutually exclusive, you can just take if you're doing 2 at the same time like we did with the blood types, you can just take the probability of one and add it to the probability of the other. But if they overlap, you have to subtract out that overlapping part. Again, this will make more sense when we look at it. So let's look at some things and first determine, are they mutually exclusive or not? So is, oh, this is exactly almost what I just said. So are these mutually exclusive? Selecting a female student, selecting a student who's a junior. Are those mutually exclusive or not mutually exclusive?
Not.
Not, because you could be both at the same time. So these are not mutually exclusive because you could be both. So not mutually exclusive. Here goes my pen again. I don't know why it does that. There we go. So not mutually exclusive because you could find or you could have a female junior student, somebody who's both. Randomly selecting a person with type O, randomly selecting a person with type O. Are those mutually exclusive? Yes.
Yes.
Because you can't have the same, you can't be type O. Type A and type O cannot occur in the same person. Okay, that would have to be 2 different people. So they can't happen at the same time. They could happen in the same study with different people, but they couldn't happen in one person. Now, if they said, could you be type A and negative? Yeah, because you could have A negative, but you can't be type A and type O. You're one or the other. All right, next one is rolling a die and getting an odd number and rolling a die and getting a number that's less than 3. So can we have odd and less than 3? Are those mutually exclusive?
No.
Okay, what example can you have both at the same time?
Well, one's an odd number and it's less than 3.
There you go. One is odd and it's less than 3. So these are not mutually exclusive because there's something that can be both. One is both odd and it's less than 3. So these are not mutually exclusive events. You can be both at the same time. Even though there's just one example of it, it's still, that's all you need. You only need one. If there's one thing that doesn't, that could be both, then it's not mutually exclusive. Okay. And then last but not least, we have randomly selecting a person who is under 21 and randomly selecting a person who's over 30. Are those mutually exclusive?
Yes.
Yes. Because you can't be mutually exclusive because you cannot be less than 21 and greater than 30 at the same time. So mutually exclusive means they can't occur at the same time. If you think of it in everyday terms, if somebody has an exclusive relationship, it means that they're not dating somebody else. So exclusive means not at the same time as the other. So mutually exclusive, like both of them can't happen mutually. Let me clear this out. This has gotten kind of messy. All right. So in this case, we've got research and development centers at U.S. Steel, Alcoa, and Bayer Material Science. Now, we're thinking of these as like full-time jobs. People aren't going to be employed at both places. So what's the probability that somebody is employed by either U.S. Steel, I'll just call that S, or Alcoa? What's the probability that they're either at U.S. Steel or Alcoa? And what would I have to calculate to get that probability?
You can add all 3 of the numbers to be your denominator, and then
Perfect. Okay, so all 3 of them, 750 and 250 is 1,000. So this is 1,110 total. Okay. And then what?
you'd add Steel and Alcoa to be your numerator.
Okay, so one or the other of these, that's 860 people that are employed at either U.S. Steel or Alcoa. So I just count both of them. Another way you could think of it is 110 out of the total plus 750 out of the total. Again, I like to just add them first and just put them on top, but the formula says take the probability of one, then the probability of the other, and add them together. But I don't have to worry about any overlap because these don't occur at the same time. So I just take each of these numbers, add them up, I'm good. And then you would reduce this. I think it just reduces to 86 out of 111. This case, you might probably just put that as a decimal, would probably be better. Let me see what they did in the book. Let me cheat here. No, they just left it 86 out of 111. Okay, so the next one, and let me tell you, this is really how I like to give this problem. You will see one of these on the exam. I really like this in table form because I think it's very logical, very visual. So I like to give it in this table form when I ask one of these questions. So in a hospital unit, there are 8 nurses, 5 physicians, 7 nurses, and 3 physicians are females. If a person selected, find the probability that the subject is a nurse or a male. Okay, so probability nurse or male. So when I look at these, what am I looking at for the nurses? Where's that at? And remember, these are columns, these are rows. Columns hold things up.
The first row.
So the first row is nurses, right? Those 7 females and that 1 male, those are the nurses. Who else should I look at though?
The doctor, the male physicians.
So this male physician, these two male physicians that I didn't count, right? So we're going to look at this column as well as this row, right?
Yes.
Okay, but you kind of said it already. You said we only need to look at the two physicians that are males that we haven't counted yet, right? We don't need to count this male nurse again just because he's male, because we already counted him with the nurses. So what the formula does, I'm not really crazy about the formula. I like to just look at it again at the table, look at it visually, and this is how I'm going to give it on the exam. So the formula, I'll show you what the formula does, and then I'll show you what I would do instead. So the formula says, take the probability that you're a nurse, so that's 8 out of the 13 people. Then take the probability that you're a male, that's 3 out of 13 people. So they did the 8 and the 3. But then subtract out that one person that's an overlap in both categories, that one male nurse. And so 8, 9, 10, 11 minus 1, you get 10 out of 13. My thought on this is if you've got something very visual like this, why not just not count that male twice? You know, why not just count what you have and say, okay, it's 7 plus 1, that's 8, 9, 10. So you just have 10 out of 13. Just don't count that male twice, that male nurse twice. I mean, either way you do it, you get the same answer, but I like to just think of it this way and not worry so much about doing it by the formula. So either subtract out the one that you double counted or just don't double count it to begin with. Let's do another one of these. What's the probability that, let me get rid of this so that it's not messy. Actually, I don't need to do that. Let me just put the slide up here again. So let's change the question. So instead of this question, let's ask a different question. What's the probability that you are a nurse or female? Well, what would we look at in the table?
The first column in the first row.
First row, and that's the nurses, and first column, that's the females. I'm not even going to go down to the totals because the totals don't really help me that much. So I have 7 female nurses, 3 female physicians. I have 1 male nurse. So I've circled up everybody that's either a nurse or a female. Well, that's 7, 8, 9, 10, 11 people total out of the 13. Again, I could do 8 plus 10 and then subtract out the 7, but I prefer to just say, well, it's 1 plus 7 plus 3 for 11. So however you want to do it, but this is absolutely how I'm going to ask it on the exam. I'll give you a table and I'll ask you an or question like this. Let me do. So the next thing that we're going to talk about is conditional probability, or independent events rather, which is going to lead us into the conditional probability. But what are independent events? Well, independent events are things that don't affect each other. So if I roll a die and then I roll the die again, those are independent events because the die doesn't remember on the second roll what it got on the first roll. So they're independent from each other. Now, dependent is when one thing affects another. So this would be like roll a die twice. Not going to affect each other. They're independent of each other. But let's say I draw a card and then I draw another. And I keep this one out. Well, that's going to affect the next draw because when I drew that card out and I left it out, now I've only got 51 cards left. Also, you have to take into account what you drew out. So say you drew out a heart, you now have less hearts than you did before. So those affect each other. Those are dependent on each other. So if the first thing you did affects the second thing that you did, those are dependent on each other. If it resets in between, like a die rolling doesn't have any brain, it doesn't know what it got the first time, they're completely independent of each other. Or if you say you roll a die and you flip a coin, you know, the coin doesn't have any idea what the die did or care. They're completely independent of each other. So what does that matter as far as doing problems? Well, in both cases, you notice in both cases that what you do is you multiply the probability of the first thing and then you multiply the second probability of the second thing. All this means is that if they're dependent, when you do the second probability, you have to take into account that the first thing happened. So that bar right there means probability of B given A happened. So it's just saying when you do that second multiplication, you have to base this probability on the fact that A already happened. So let me show you a couple that would be like what you would see. Okay, so this one, it says a coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on the die. Well, I just mentioned these are completely independent events. The coin does not know what the die did or vice versa. So they're completely independent. So all I have to do is figure out what's the probability that I've got a head, and I just multiply that times the probability that I'm going to get a 4. They're completely independent of each other. I just figure out each one, multiply it, and I've got my overall probability. So what's my probability I'm going to get a head? 1 out of the 2 sides. What's the probability I'm going to get a 4? 1 out of the 6 sides of the coin, or 6 sides of the die, rather. And so overall, that's 1/12. If you want to think of it in sample space terms, here's everything that could happen. Heads with a 1, heads with a 2, heads with a 3, and so on. And then tails with a 1, tails with a 2. Only out of all these 12 options, only one of them is what we want. So 1 out of the 12. You guys okay with that one? This is a good time to stop too and talk about, good. This is a good time to stop too and talk about, you should have a fraction button on your calculator somewhere, and it will come in very handy. So somewhere on your calculator, you should have a fraction button. On my calculator that I'm using right now, it has N/D. And when I push that button, it actually puts up a little thing with boxes in it that I can put my fraction into. The TI-30s that a lot of people have, TI-30, TI-31, I can't remember what they are. They're the ones at the bookstore. Well, nobody's going to the bookstore right now, but there's some of them that'll have it like an A, B over C button. This one that I have, I just fill in these little boxes. If you have one of these, if you wanted to put in like 1/2 times 1/6, you'd do 1, push that button, 6, and then you do times, whoops, I did it backwards, but you get the idea. And then you do times that button, 2. So if you wanted to do 1/6 times 1/2, you just push that button in between the numerator and the denominator to tell it it's a fraction. So 1 fraction button 6 times 1 fraction button 2, and then it should come out, I think that calculator that does that, it comes out, it looks kind of like this. That means 1/12. So it's really helpful for you to know where your fraction button is on your calculator. If anybody has any questions on it, don't hesitate to email me and ask me. I would say, though, that the fastest way to figure it out is just type in, just Google your calculator. You know, so like I have a TI-34 multi-view. So I would just Google TI-34 multi-view fractions, and you'll find videos on YouTube and such that'll show you how to do it. Yeah, that's a lot more helpful. Oh, and the other thing that's helpful is most calculators also have a button that will switch you back and forth from fractions to decimals. Some of the calculators say S to D, and some of them say F to D. This means standard to decimal, and this means fraction to decimal. So if you're trying, if you're in decimal or fraction form and you need a decimal, you just hit this button. You usually have to do a shift beforehand, so like second and then this button, and it'll shift it back and forth. So it'll take it from decimal to fraction, fraction to decimal. If you've got a graphing calculator, like a TI-84, it's under the math. So if you go to math, if you push the math button, which is like the third one down on the left, there's a switch to fraction and then there's a switch to decimal. So the graphing calculators don't actually do fractions, but you can do it in a decimal and then switch it to a fraction. So on the graphing calculator, you push math and then you have a selection that looks like this. It's like a little arrow. And then you have another one that looks like this. And so you can switch it to a fraction or switch it to a decimal if you've got it in one of the other forms. But the TI graphing calculators don't actually do fractions like a lot of the other scientific calculators. Anybody have any quick questions on that? Okay. I'm not going to do this Harris poll because I think it's a horrible example. So we're going to skip that one. This problem I'm not super crazy about either, but I'm going to go ahead and do it because I think there might be one in your homework on it. But I'm going to kind of oversimplify it a little bit. So I'm going to change this question. It says, in a recent survey, 33% of the respondents said that they feel they are overqualified. I'm going to just change that to 1/3. 33% isn't exactly 1/3, but we're just going to change that to 1/3. And then it says, of these, 25% said that they were looking for a new job. I'm going to change that to 25% instead of 24% because it'll make this problem easier for me to show by a long ways. So in a recent survey, 1/3 of the respondents said they feel they are overqualified. So I'm going to make a little, like a little rectangular bar here. And what we're saying is if we split that into 1/3, into thirds, these people think that they're overqualified. These people think that they're not overqualified. So overqualified, not overqualified, not overqualified. Then it says, of these, meaning of the ones that think that they're overqualified, 25% said they were looking for a new job. So we're taking this section, we're not worrying about these sections, we're only looking at the people that said that they were overqualified. Let me use a different color, that'll make a lot easier to see. Of these ones, we're going to mark it into fourths. And of those, 1/4 of them say that they're looking for a new job. So these people are not looking for a new job, not looking for a new job, not looking for a new job. So this little section down here are the ones that are looking for a new job, and they also thought they were overqualified. So those are the only people in this whole scenario of people, is this little section down here that thought that they were overqualified and they're looking for a new job. Well, if we continue this split here, what is that? Well, we've now got 12 sections, and out of the 12, only one of them is what we're looking for, 1/12. In other words, I took 1/3 that were overqualified, and I multiplied it by the 1/4, the 25% that thought that they were overqualified. So I get 1/12. So you just take the first one and you multiply it by the second one. Not crazy about this question. What I like to do with this is to do it with the table, the same way that we did before. Actually, this one I probably won't ask on the test, but you probably see it on the homework. But all you have to do is just take the percentage that we're given and then multiply it times the percentage of those people in that category. So like in this case, they did 1/3 times 1/4 or 0.33 times 0.24. Does anybody have any questions on that one? Okay, again, this is probably homework, probably not going to see something like this on the test. And that's it for 4.2. We're ready to get into 4.3. Does anybody want to stop, pause, ask any questions, clarification, or anything before we do new topic? Okay. So the next thing that we're going to talk about is conditional probability. And this is, conditional probability is like we were talking about. Let me go back to this other slide. That's what they had on this other slide. It's where you have to, where was that at? It was when we were talking about the mutually exclusive. Let me put this up here. Okay, so it's what they were talking about. Nope, wrong one. Shoot, just a second. It's when they were talking about independent and dependent. Here it is. Okay, so conditional probability is this situation where if two things are not independent of each other, then on the second or subsequent events, you have to take into account that the first one already happened. So again, this means the probability of B given A already happened. Okay. Again, I don't really like to think of this in this way. This formula is, I think, confusing for people. So let me show you exactly what kind of problems you're going to see from me on this, and mostly on the homework too. So let's say I asked you, what's the probability of all right, let me give a situation here. So let's say we've got several chips in a basket, okay? So you'll either see it this way or you'll see it in a table, which we'll do a table here in just a minute. So let's say there's 9 chips, and out of these chips you've got 4 that are blue, 2 that are yellow, and 3 that are red. And I ask you, what's the probability that you get a blue, then a red? Well, I have to, when I do this, when I do the red, if I don't put the blue one back, I have to take that into account. So I have to do the probability, on the second one, I have to do the probability that I get a red, given I already took a blue one out. So what's the probability that I get a blue on the first draw? Can you guys tell me that? And again, this is not replacing. So
That's 4 9s.
4 9. So there's 4 blues, right? So 4 out of the 9 are blue. But what's the probability that I get a red, given I already took out one of those blues?
Is that 3 out of 8?
Yep. So I still have 3 reds because I didn't take a red out, but I now only have 8 total chips because I took one of the blues out. So I can't say 3 9ths, I have to say 3 8ths because I have to take into account that this already happened. So it's not just a 4 9ths times a 3 9ths, it's a 4 9ths times a 3 8ths. Let's do another one. What's the probability? We'll do a couple more of these. What's the probability that I get red? So I like to put these little spots to kind of keep track of it. So red. I got to take the probability that the first thing happens times the probability the second thing happens, but I have to remember on the second one that this one already happened. So what's the probability I get a red the first time?
3 out of 9.
Yep. And then I've taken one of those out, Okay, so this blue one's here because we started over. Okay, so we still have our 4 blue, our 2 yellow, our 3 red, but I've taken a red out on the first draw. So that guy's gone, or one of those is gone. What's my probability of getting a red the second time now?
2 out of 8.
2 out of 8, perfect. So I have to take into account that I took one of the reds out already, so I have to lower the 3 to a 2, and I have to also keep into account that I took, left a total chip out, so I don't have 9 chips anymore, I only have 8 chips. So it's 3 9ths times 2 8ths, not 3 9ths times 3 9ths. I can't use that same probability each time because what happened here on the first draw affected the second draw. So I have to adjust. And then you'd multiply these and get the answer. So this is what, 12 out of 72, and then you'd have to reduce it 1/6, right? 12 was in 72 6 times, yes. This would be 6 out of 72, which is 3 out of 36, which is 1 out of 12. Okay, so this has a 1/6 chance of happening. This has a 1/12 chance of happening. All right. And you can do that for 3 things in a row. So like, let's say I wanted to do, here, we'll just adjust this one that we just did. Let's say I wanted to do, instead of red, red, let's say I'm going to draw 3 out, and I'm going to do red, red, yellow. So what would be the probability of red, red, yellow? We would have to add another box or another thing here for yellow. So red, red, yellow, 3 9ths, 2 8ths, and then what's the chances that I get a yellow on the third draw? I've removed 2 reds.
2 7s.
2 out of 7. So again, I still have 2 yellows because I haven't taken any yellows out, but now I'm down to 7 total. So if you're not replacing, this bottom number is always going to go down. And then everything on the top, you have to see, did I take one out already? So this went down to 2 from 3 because I took a red out. But the yellow's still at 2 because I hadn't taken a yellow out yet, but the total's at 7. So then you just multiply all 3 of those. So 3 times 2 times 2 is 12 over, I don't know, whatever that is, 9 times 8 times 7. So you'd have to multiply those out, reduce it. The nice thing though is if you do it on your calculator as a fraction, it'll reduce it for you. So that's why I very much encourage you to figure out how to use the fractions on your calculator. Let me know if you can't figure it out. I'll be happy to help you. Okay, so where were we at? 4 3.
Quick question. How do you write the final answer?
You can write it either as a reduced fraction or as a decimal.
So you just list.
Yeah, so here, let me clear this up. So what do we have? Well, I guess I don't have to clear up. I'll just focus on this one right here. So say this was your problem, right? You're doing this one. So you get to your final answer and it comes out 12/70 seconds. You could either reduce it and enter your answer as 1/6, or you can take 1 divided by 6 and write it as 0.167. On Connect Math, it usually tells you to go 3 decimal spots. So this is 1.6666666. So you're going to round the third decimal up to 7 because it's got a 6 after it. Because it's 1.66666. Does that make sense? So this gets rounded up. Okay, you're okay with that? Okay, good.
And will it? Oh yeah. Just didn't know. Did they specify if it's a fraction or a decimal?
What it will almost always say is it'll say write as a reduced fraction or a decimal to 3 decimal spots. It'll give you an option. And technically, if you were doing this just away from the computer, it would be perfectly fine to say 16.7%. It's just Connect Math just says fraction or decimal. But it would be perfectly appropriate to say the probability of this happening is 16.7%. They all mean the same thing. So
yeah, that's what I was asking, if there was a format that was preferred.
Yeah, it's at least they allow you the 2 different ways, if not the third. I think they just worry that the percentage will get confusing. I hate this next question, this parking tickets one. I'm going to skip that one because I'm pretty sure there's not one like that in your homework, and I don't like it, and I won't ask it that way. So we're going to just forget that one. All right, so let's do this one. This is how, the way I just showed you with the coins and such, that's one really good way, one way that I really like to ask the question. The other way I really like to ask this question is this way, in the form of a table again. So we'll do several of these because these can get these are a little bothersome for folks. So it says, we have a recent survey, 100 people, if they thought women in the armed forces should be permitted in combat. These are the results. So males, females, yes, no, and I have no idea if this is a valid study or they just made it up. But, out of the 100 people, 32 males said yes, 18 males said no, 8 females said yes, 42 females said no. And the question that they're going to ask is, what's the probability? This is their question on the next slide. What's the probability that they said yes, given that they're females? So let's step back from this for a minute and think about this. Even though it's a study, think of it more as a classical problem. So say I took this study and I represented it in a box full of chips with 100 chips. All these male yeses, I put a chip in the box that on one side said male and on the other side said yes. Okay, or I could make them blue chips with yeses on them for male yes, whatever. Some way to represent that it's a blue yes, or a male yes rather. And I would have 32 of these in the box. Okay. Then in the box I would have 18 chips that on one side said male and on the other side said no. So I'd have 18 of those chips in there. I would have 8 chips that on one side said female and on the other side said yes. And then I would have 42 chips that said female and on the other side said no. So in my box, I would have 100 chips. You guys okay with that? Be this box full of 100 chips. Shake it up. Put them in a bag, put them in a box, shake them up. There's 100 of them in there. And somebody said, okay, what's the likelihood I'm going to pull out a female yes? Well, that'd be 8 out of 100 because there's 8 of them. But that's not what I'm asking here. What I'm asking here is, what's the probability that I get yes, given only the females? Given that that I know that in the box is only females. So what I'm saying is I'm completely changing what's in the box. There's not 100 chips in the box anymore. I'm not looking at the males anymore. I'm only looking at the females. So how many total are there now? If I take all these males out of the box, they aren't even in there anymore. I dump the box out on the table. I sift through it. I take all the chips out that say male on them, and I just put back in the female chips. And you said 50, right?
Yeah.
Yeah. Now there's only 50. There's only the female chips in there now. And how many of those are yes?
8.
8. What I'll give for an answer on this a lot is 8 out of 100. But they're not taking into account that you dumped out all the male chips. You're not even looking at those. So you're given in your box now only the female chips. So this number here, it's actually kind of visual. Think of this as like your division bar. And this second thing right here is your new denominator. So yeses, the female yeses, but only given the females, and there's 50 females. So basically, if you don't want to, draw this whole picture, when it says given females, you're crossing out this row. You're only given the females. This is all that's in your box now. 8 out of 50. We don't have 100 total anymore. So everybody goes, oh yeah, I get that. And then we do another one and they mess it up. So let's do some different ones. What if it was probability of male given yes. Oh, hold on a second. I'm going to do something real quick before I do that. We're going to do that same problem, but I want to get rid of what I have written on the table. Okay, so probability male given yes. So what I want to know here is, what am I given in my box now? Dumped everything out on the table. What am I going to put back in the box to pick from?
Just the male chips?
Nope, and that's the same. You made that classic mistake. You are in wonderful company.
Well,
We
that's
don't-
good.
Yeah, very good. So what do I have left? Do I have the male chips, or do I have the yes chips?
Yes, chips. That's
Yes
cool.
chips. They can do this either direction. Here it was yeses given females. Now it's males given yeses. So we're only given the yes chips. This time we're crossing out a column, keeping a row. I'm sorry, crossing out a column and keeping the other column. Okay, so we're only looking at the yeses, not the no's at all. So only these in this column. So what's my new denominator?
40.
40. Yep, it's not the 50 males, it's the 40 yeses, because that's what was given. So this number right here is going to be your denominator. And then how many of the males? Once we know we're only looking at the yeses, what's the chances of picking out a male?
32.
32. And then again, you'd reduce these. So like this would end up being 4 out of 25, or you could say 0.16. This one, I don't know what that is. Let's see. 32 out of 40 would reduce to, that would reduce to 4/5. Or you could put 0.8. So either one would be fine. All right, let's do one more. What's the probability that, let me get rid of this. Did you guys have that written down before I started to erase it? I'm sorry. You guys good? Okay.
Yeah.
Okay. So I'm trying to get back so my table's not all written over. There we go. Okay. So this one came out to be 32 out of 40, or 4/5, or 0.8. Okay. This one is this one. So now let's do probability of, I don't know. Let's do no's given male. So what would be, what am I going to keep? What am I going to throw out?
The yes column?
So do I want to throw out, this is my given, remember? This is what I keep in my box. So am I going to throw out a column or a row? Or what am I going to keep, a column or a row?
You're going to throw out the female row?
Throw out the female row. So this is no's given that I only have the males. So I'm going to throw out the female from this survey. Only keep the males. It is confusing. It doesn't say male given no's. It says no's given males. This one is your denominator. The one after the bar is your denominator. So there's 50 males, right? How many no's?
18.
18. Let's just flip that one. If it was males given no, that would be given the no's, so no yeses, that would be 18 out of 60. So see, it's the denominator that matters. It's still the male no's, so it's still 18, but it's what you're given. Here you're only given the males, there's 50 males. Here you're only given the no's, there's 60 no's. What do you guys think?
Makes
You
sense.
don't like it. It kind of makes sense.
I'm
You don't
good.
have to, you don't have to like it, but, and remember there's going to be, I like to do, so there'll be 2 table problems on the test, at least 2 table problems. And one's going to be a probability of this or that. The other one's going to be probability of this given that. So there'll be one of each of those kinds of problems, and they're different. This is the one where you circle up both of them and then just don't count the overlap. This one is where you throw out everything that you're not given. So they're different types of problems, and you'll see both of those on the test. So make sure that you kind of review that. There's review videos in D2L too, if you guys haven't noticed that. So I did some live reviews with my class. Okay. So we're at 12. We're actually doing pretty good. I think we'll be done about by 12:30 at least, because all we have to do is 4-4. We're almost done with 4-3. And so we're going to do finish up 4-3. And sorry, my son doesn't understand I'm in class. I don't know how many times I can tell him, but I can have a chat with him. Okay, so we have ties, and I'm going to do this one because this is a really good example of a complement that isn't really that great of an example of what we're working on in section 4.3, but it is a good example of the complement idea and how you may, when you're doing your homework, you'll want to watch for things where doing the complement is easier than doing the actual problem, okay? So this question is talking about bow ties and regular ties. So we'll call them bow ties and not bow ties. So that'd be like a regular tie. And it says the Neckwear Association of America, if you didn't know there was a Neckwear Association of America, I think that's a real thing, reported that 3% of ties sold in the United States are bow ties. So we all kind of know that bow ties aren't as common. You see people wear them, but not as common as just a regular tie. So they want to know if 4 customers who purchased a tie are randomly selected, find the probability that at least 1 purchased a bow tie. Okay, so in other words, if you think of the sample space, here's the things that could happen. You have somebody come in, 4 people come in, and none of them have bow ties. Or thinking along the lines when we were doing like the boys and girls in a family, you could have the last person has a bow tie. Or the 3rd person has a bow tie, etc. Okay? Then though, you could have 2 people that buy a bow tie. So NNBB and BNB. So 2 bow ties and 2 non-bow ties, and you could, try to figure out all the different ways for that. Then you'd have to think about what if it was 1 did no bow tie, 3 did bow ties, and again, figure out all the different ways for those to shift around, all the way up to everybody bought a bow tie. So that's a lot of different things that are going on there. So it says at least 1 purchased a bow tie. So that would be everybody but that one. So you would, at least 1 purchased, that would be all of these things. We'd have to figure out how many of those that there are. Is everybody okay with that? Like the reasoning behind it?
Yeah.
That would be a pain, right? To figure out how many of all of these there are. So easier than that, and easier than calculating all of these out, the complement of at least 1 purchased a bow tie is no bow ties. So the probability of at least 1 is the complement of no, so at least 1 bow tie would be the complement of no bow ties. And it would be a lot easier to figure out the probability of getting no bow ties and then subtracting it from 1 than it would the other way around. So here, The biggest thing with this problem, or the biggest help I think this problem is just to show you that when you're doing your homework and it asks you to do something and you're like, holy cow, that would be a whole lot of different things I'd have to figure out. Pause for a second and say to yourself, wait a minute, could I figure out the opposite of that, the complement of that? Would that be a lot easier? And if it is, do that and then just subtract your answer from 1. So that's what we're going to do here. We're going to just calculate the probability that everybody that came in got no bow tie. So first person, no bow tie. Next person, not a bow tie. Third person, not a bow tie. Fourth person, not a bow tie. And we just multiply those out, get your answer, but whatever we get is going to be the complement of what we want. So what's the probability that the first person didn't get a bow tie? 0.97, because 3% chance that they do get a bow tie. So a 97% chance that they didn't buy a bow tie. So I'm going to pause there. Any questions on that? That's a lot of stuff going on. Are you guys okay with why we're doing the complement instead of just the regular?
Yeah.
Because there's all these different ways the regular one could happen. At least one would be 1 or 2 or 3 or all of them. And there's a whole bunch of ways for that. Okay, so 97% chance that they don't buy a bow tie. Are you guys okay with that? That's the
Yes.
3%. Okay, and then every single one of these is the same because these are really independent events. Because we're talking about a whole population, so it doesn't really matter that one person came in and, it doesn't really change the population, that 97%. So we just multiply that all out, and that gets us 0.885. So that's the probability of no bow ties. But that's the opposite of what we want. So we're going to do 1 minus the probability of no bow ties. And that gets us 0.115, and that's the probability that we get at least 1. So greater than or equal to 1, I should say, bow tie. So the probability that you have greater than or equal to 1 bow tie is 0.115, because that's everything else. This happening was a 0.885 chance, so that makes this a 0.115 chance. Because those are the only 2 things that can happen. What do you guys think? Okay. There's probably be maybe a question or 2 in your homework that if you keep this in mind, it'll probably help you on. Not something, again, I'm not going to throw something like this at you at the test. This would be a homework problem. It's kind of like when you're doing your homework, it's kind of like being, at a practice. Think of something like running or swimming where you have to do, a lot of miles to practice. Just because you swim your race that you swim is a 100-meter race, or the race that you run is a 100-meter, sprint, you don't go out and just practice 100-meter sprints. You go out and you practice, higher distances, several of them in a practice and so on, so that when you get to the easier, get to the 100-meter sprint, it seems easier. So that's kind of like homework. Homework is going to be harder than the test is going to be. You're going to see stuff on the homework that you won't see on the test. So, when you're getting ready for the test, make sure you watch the reviews, because in the reviews, I'll emphasize the important, what types I'm going to have on there. So this case, this isn't going to be on a test. This is just homework. Okay. The last thing that we have to talk about is section 4.4, which is counting rules. And remember, 4.5 is already recorded, so you can watch 4.5 also. 4.5 just kind of wraps up everything. It kind of takes 4.1 through 4.3 and 4.4 and merges them together, because 4.4 is actually a little bit different. Remember, in all the other sections, we've been doing probabilities. So in section 4.1 through 4.3, everything we were doing was, what's the probability of this? What's the probability of that? In 4.4, we're doing counting. And then in 4.5, they merge the counting with the probabilities. So in 4.4, why do we stop and take a pause on counting? Well, when we're doing our probabilities, remember this bottom number is always like the total number of ways something could happen. And then the top is the number of ways what we want can happen. Sometimes you can't just count these. You can't just physically look at it and count it. It's too much. So these counting rules are going to help us figure these numbers out when we have lots of choices that could happen. So we're going to pause and we're going to talk about the fundamental counting rule or the multiplication of choices, and then we're also going to talk about what are called permutations and combinations. So multiplication of choices says that if you have a sequence of events that are occurring and you want to know how many total ways there are, then you just have to figure out how many ways for the first and how many ways for the second, and then how many ways for the third, etc. And you just keep going until you get your choices. So I'm going to start with something that we're all pretty familiar with, and we're going to do another example too, but I'll start with this one. So say you're at an event and they have a buffet, if ever they happen again. Not sure if we're ever going to be able to have large events again. Okay, so we have a buffet, and at this buffet, say it's a wedding or a you know, some sort of a work event, and at the event they have 5 different main courses you can pick from. Actually, let's make that 3 because it's usually not that many. So maybe you have like a chicken, a beef, and a vegetarian. So you have 3 main dishes that you can pick. You have 6 sides that you can pick from, and you can pick 2. Okay. And then let's say there's 4 desserts, and there's 2 drinks. You know, maybe you can get tea or lemonade or something like that. Okay. So how many different ways could you pick your meal? You know, that's not really a lot of choices. I mean, that's a lot less than any restaurant has. You know, we're talking about a buffet, so it's kind of limited. 3 main courses, 6 sides, 4 desserts, 2 drinks. That's not that much to pick from, we wouldn't think. So how many ways can you do that? You are going to be amazed at what a big number this is. Because for the main dish, we have 3 things that we can pick from. With that main dish, how many sides do we have to pick from?
6.
6. So let me kind of, you know, write this down off to the side just a little bit. So that would mean like you could do, you know, say the sides are, you know, a salad, mac and cheese, you know, some different things. So you could have like chicken, salad, chicken, mac and cheese, chicken, green beans, chicken, you know, whatever. You can do that. You're gonna have 6 different ways that you can have chicken with a single side. Then you're gonna have 6 ways you can have your beef with a side. Then you're gonna have 3 ways that you can have your vegetarian with a side, for a total of 18. So we've only got main dish and 1 side, and we're already at 18 different possibilities. Does that make sense? Okay, with that, so like be chicken, you know, chicken, you know, like I said, you've got 6 different ways for each main dish that you can pick the side. Are you guys okay?
Yeah.
Yeah?
Yes.
Okay. Now this next one, you guys are going to probably want to ask me a question. So we're going to pick a second main dish here. So here's our side 2. How many ways are there to do that?
Is that 5? Or are you going to include 6 if somebody wants 2 of the same?
There you go. So can we pick the same or not? Because if we can pick the same, If we can pick 2 orders of mac and cheese, you know, you love the mac and cheese, so you say, I want mac and cheese, that would be 6, 6, right? Let's say no repeats. So you can't even, no matter how much you like mac and cheese, you can't get two servings of it. So you got to pick something different. So that only makes it 5, right? But that's important. So if you were doing a problem in the book, you'd have to make sure that you pay attention to whether you can repeat it or not repeat it, or if it gets put back, or, you know, when you're talking about cards, does the card get put back or not get put back? Okay, so side 2, only 5 different ones because you have to pick something different. Then desserts, got 4. Drinks, you've got 2. And we're just talking main dish, couple side dish, desserts, and drinks. And if you multiply that out, believe it or not, there are 720 different ways to do that. At a simple, you know, little buffet with a very limited number of options. You still have 720 different ways you could pick your meal. Kind of crazy. So when you're, you know, when you're standing in your closet and you can't decide what to wear, and all you have is, you know, well, I've only got 7 shirts clean that I like and 4 pairs of shorts that I like to wear today, that's still 28 options. So, you know, when you can't make up your mind what to take on a trip, what to put in your suitcase or whatnot, or what to wear for the day, you know, you can give yourself a little bit of a break because those multiply up pretty darn quickly. Okay, so now let's look at theirs. They have a really quick question, or a really quick problem here, pretty similar to what we just did, that talks about paint types. And again, if you think about an actual paint store, this is very oversimplified. So the types of paint you can have at this, from this brand, is they only have 7 colors: red, blue, white, black, green, brown, and yellow. Only 2 types, latex and oil. Only 3 textures and only 2 uses. You know, this is completely oversimplified. There's millions of different colors you can get. Well, maybe not millions, but thousands of different colors you can get with the different brands. And then the types, there's more than just latex and oil. There's ones that are combos. There's ones that are, you know, just all kinds of different. There's more than 3 textures in a regular paint. And there's outdoor, there's indoor, there's multi-use. There's, you know, ones that are specifically for doors, ones that are specifically for floors. You know, so there's all kinds of stuff going on here. But even just at this, if I just have this amazingly oversimplified version of paint, I still have 7 colors, 2 types, 3 textures, 2 uses. That's 84 different paints. So when you go to, you know, Lowe's and you try to go, you know, try to find the paint that you want, even if it's something simple like, oh, it's this one brand of spray paint that I want in this color with this texture, it's almost impossible for them to keep everything on the shelf. Just this oversimplified thing with one brand, they'd have to have 84 different things on the shelf in order to cover all of those. So again, when you go and you're like, how come always what I want isn't there? Well, because it's really hard for them to keep things stocked with all the different varieties. That's why I don't, if you've never done any painting or anything, that's why they have what they call base paints, and then they tint them, because then all they have to do is keep the base paint on the shelf. So they keep the base paint that's like white with the correct texture and the correct type and use, and then they tint it the color you want, because then they only have to have that one thing on the shelf. All right, any questions on that thing? Okay, we are going to now talk about factorials, permutations, and combinations. So the factorials, I'm going to explain it, but I'm going to show you a way on your calculator to do it an easier way. So what a factorial is it's the product of all the positive numbers from 1 up to a number. Okay, actually it's usually from the number down to the number. So if I was going to calculate, say, 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Why is that important? Well, think about the side dishes. When you start picking something but not replacing it, that number keeps going down. So if somebody said, take these 6 side dishes and put them in order, well, the first thing that you picked, if it was 6 side dishes, the first one you'd have 6 ways. Then the next one, if you've already placed one, you have 5 places for the second, or 5 choices for the second place, 4 for the third, 3 for the fourth, 2 for the fifth, and only 1 for the last spot. So this is where factorials come into effect in this counting an awful lot. So they have this is actually a mathematical symbol, that exclamation point thing. It means take that number and multiply all the integers down till you get to 1. On your calculator, you probably have a button for factorial. Again, I have the TIs somewhere on your calculator. For the TI calculators, it's usually under a button called PRB. Whoops, I don't know why I put PRM. PRB. So if you look on your calculator and you see a PRB, does anybody have a graphing one, a graphing calculator?
I do.
I have a TI 83 plus.
Okay, so let me
There's
see.
a TIA for it.
Okay, so on the graphing calculators, push math again, which is the 3rd button down on the left. And then at the top on the far right is PRB. Anybody watching this recorded, whatnot, if you've got most of the TI calculators, it's a PRB button. On the TI 34, for instance, it's just on the main screen, there's a PRB button. But once you push that, the TIs push math, then choose PRB. You have something that looks like NPR. We're going to use that in a minute. You have NCR. We're going to use that in a minute. And then you have this button. So like if you wanted to do 7 factorial, you just push 7, math, PRB, pick the factorial, hit enter. You should get if you put it in right, you should get 5,040. Is anybody having problems finding that? Okay. If you are and you need it, just Google your calculator, you know, TI-34 or Casio, blah, 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 factorial. It's spelled like this. And just Google that, and I'm sure you'll find a video that'll show you how to do it. Okay, or send me an email, and I'll try to find it for you if you're having a hard time. All right, so why do we need to know that? You know, this is why it comes into play. And the first thing that we're going to talk about are permutations. And the next thing we're going to talk about are combinations. So when we're talking about a permutation, it is an arrangement of objects in a specific order where the order matters. So this doesn't make a lot of sense until we see one. So let's see one. Actually, let me just make one up because I don't like their first example so much. So let me make one up. So let's say you were deciding how to place books on a shelf. And it matters to you what order are up there. You're trying to, you know, put them up there so that you can find them. You have a specific order you want to put them in. And let's say you have 10 books that you're picking from, and your shelf will hold 6 books. How many are you choosing from? Well, that would be 10. And how many are you choosing? That would be 6. So you're choosing from 10 and you're placing 6 up on that shelf. And you're saying, if I put them in a different order, I'm going to call it a different thing. So if I put, you know, my favorite novel, then my favorite, you know, anyway, so they're different order. So putting, let's just call them books A, B, C, D, E, F, G, 3, 5, 6, 7, 8, 9, 10. So I have these 10 books, and if I put A, B, C, D, E, F, that's going to be different than if I put F, A, B, C, D, E. So even though it's the same 6 books, I'm going to call it something different if it's in a different order. this right here would be a 10p6. And in order to calculate that, I'm going to do n factorial on top. That's the 10. And on the bottom, I'm going to do n minus r factorial. So I'm going to subtract the two numbers, 10 minus 6, and I'm going to do a factorial of that. So that would be 10 factorial over 4 factorial. Okay, I just rambled on for a really long time without pausing. Do you guys have any questions on the setup here? Not the calculation so much, but do you go okay with the setup? That you're picking from 10 books, order matters, and you're going to pick 6 of them? Okay.
Yes.
So if I'm going to calculate that, that means 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Phew, okay. Put that over 4 factorial, 4 times 3 times 2 times 1. But what can you do with a fraction if you've got the same thing on the top and the bottom, the same factor on top and bottom?
Cross it out.
Cross it out. So the 4, 3, 2, and 1 can all go, right? I mean, 1 didn't really matter anyway. But so what we're left with is 10 times 9 times 8 times 7 times 6 times 5. So that would be your answer. If you were computing this completely by hand, that's how you calculate it out. You write out the first factorial, you write out the second factorial, you cancel out anything they have in common, and then you have to multiply what's left. But here's the glorious thing. Did you guys notice when you were looking for this factorial button that you had a button that looked like that? You are more than welcome to use it. And in order to do this on your calculator, you would just type in 10, choose that NPR, and then choose 6, and then type in 6. And it'll get you the same thing that we just did up there. So if you want to try a few by hand, go ahead. But honestly, I just want you to know, I want you to recognize a permutation problem, know that it's a 10p6, and calculate it. Okay. So either way, are you guys able to get an answer for that? What are you getting?
I got 151,200.
Okay. And I hadn't calculated. Yep. And again, isn't that unbelievable? You only have 10 books that you're putting on a shelf, and there are 151,200 ways to put those books on that shelf. If we had put all 10 books, we would have had to take this times 4 times 3 times 2 times 1, because we wouldn't have had anything. We would have had a 0 left on the bottom. So that would have made it even bigger. I mean, it's unbelievable that how fast these multiply up. So there are 151,200 ways to put those 6 books out of your 10 books on a single shelf. Crazy. Okay, so the other thing that we're going to talk about, you'll notice in the permutation, the order matters, right? Let me get rid of this one just a second. So in a permutation, which we call NPR, order matters. In a combination, which we call an NCR, it's the exact same thing, but the order does not matter. And this gives you, this will be a lot smaller number. If you use the same numbers for N and R, the combination will be a lot smaller than the permutation. Because in a permutation, let's say you have the letters A, B, C, D, E to pick from, and you're going to pick 3 of them. You would count A, B, C different than B, A, C, different than C, A, B, etc. Those would all be different things. But in a combination, when the order doesn't matter, an ABC is the same as a BAC is the same as a CAB. You've got the same three things, and so they don't count as much. Here you'd have, what is that, 5, 4, 20, like 60 different, you have a whole bunch of different ways to do ABC, but here you only have one way. Does that make sense? The difference between the order mattering and the not order mattering? If you're thinking about like real life, this would be the difference between putting the books on the bookshelf or just throwing the books in your bag. So you just want to make sure you have the right 3 books to take to class versus placing the books on a bookshelf in a certain order. This one, the order doesn't really matter how you throw them in your bag. You just want to have them with you. This one, it matters because you're putting them up on a shelf. Does the difference between order mattering and not order mattering kind of make sense?
Yeah.
Okay.
Yes.
So how to remember these? The way I remember it, it's kind of silly, but the way I remember it is that combination locks are named entirely wrong. Because on a combination lock, the order matters. On a combination lock, you can't go to your school locker and, put in 20, 32, 7 and expect it to open when your combination is 7, 7, I don't remember what numbers I said, 31, 22. You have to put it in the right order. The other thing with combination locks is you can repeat. So you could have a combination that was 7, 22, 7. That's allowed on a combination lock, like a master lock. Well, that's in a real combination, a mathematical combination. You can't have repeats. So combination locks are named completely wrong because with combinations in mathematics, the order does not matter and you cannot have repeats. You can't have ABB. Once you put something in there, it's done. And the formula for this, it's very similar to the permutation, an NCR. You do n factorial on top. You still do the n minus r factorial on the bottom, but you also do an r factorial. That r factorial is how many ways, like it gets rid of the repeats. So it divides out the repeats so that you're not counting ABC separate from BAC. So that's why you have the extra thing on the bottom. But again, for our sake, you're welcome to just type that in the calculator as an NCR. Anybody have any questions with that? This is what it looks like on the slide. It's a grouping of objects where order doesn't matter. Here's the formula. And it says you could think of it as an NPR with an extra r factorial on the bottom, but I don't like that way. Just think of it like this. But we're just going to do it on our calculator. Okay, so let's look at some of their examples. So your biggest thing is to figure out, does the order matter or does the order not matter? And then just calculate it up. So it says here, suppose a business owner has a choice of 5 locations. To establish her business, she decides to rank each. How many different ways? Well, you could do this the old multiplication of choices way and just say, well, she has 5 ways to pick her first location, for her second location, or her second choice. 5 locations for her first choice, 4 locations for her second choice. Once she's picked her first 2, she's got 3 left. Once she's picked her top 3, she's only got 2 left, and then the last one goes in the last spot. Or you could think of it as order matters because you're ranking them. So you could think of it as a 5P5. She's got 5 and she's placing all 5. So whether you type this into your calculator or you type this into your calculator, you should get the same thing. You should get 20. Are you guys okay?
Yeah.
Okay. Are you guys okay with the fact that that one is a, the order matters?
Yeah.
Okay.
Yes. But you mean 120, right?
What did I say? Oh, yes. Sorry. I covered it up with my pen and then I was being lazy and not thinking. It's 120. Yeah. Yeah. 20 times 3 would be 60 times 2, 120. Yep. Okay, so this next one, it says, all right, we're going to do the same thing, but she doesn't really care what her bottom two rankings are. Let's just rank up her top 3 favorites. So same problem, it's just that instead of, the order still matters. So the order matters. And so it's a P. But instead of picking 3 or 5 out of the 5, we're only picking 3 out of the 5. Be careful when you put these numbers. Every once in a while, I'll have somebody email me and they're like, I'm trying to do this, and I know you're picking 3 out of the 5, and they'll say, I'm putting in my calculator 3P5 and it's not working. That's because this is supposed to be the total, and this is supposed to be how many you're picking from. If you flip it, you're trying to tell the calculator you're trying to pick 5 out of 3 things, which doesn't make any sense. So make sure to put that big number first. And this comes out to be 60. So you could either type it in your calculator like that, or you could think of it as 5 choices, then 4 choices, then 3 choices. But I'm not going to do the last 2 so that I don't have any numbers down there. Or if you use the formula, it's like 5 factorial over 2 factorial. So these cancel out, you get 5, 4, 3. So any of these will get you the same answer, whatever comes to mind first. All right. So this one, they tell us that the order matters, but some of them you'll have to decide whether the order matters in your homework. It says, a radio talk show host can select 3 of 6 special guests. The order of appearance is important. How many different ways can it be done? So what are we going to type in our calculator? Is it going to be a P or a C?
P.
P, because
P.
order matters. Yep. So P, because order matters. And we're going to do a 6 P3. Yep. And if everything's coming out, this should be 120 also. I don't know why they got stuck on the 120 there, but. And then the next one is a musical director. This one you might think, oh, the order doesn't matter, but it does because we're talking about musical plays, and it says, the key word here is it says the school musical director can select 2 musical plays to present next year, 1 in the fall and 1 in the spring. So it's indicating it does matter what order it is. So it matters whether you pick, you know, say you do Fiddler on the Roof and I don't know what else would be a common high school musical. Wow, you know, I have been going on the same strain when I can't even think of a second musical. What's that?
Footloose.
Cats.
There you go, Cats or something like that. So
Once on this island.
yes, there you go. Okay, so but it would matter whether you did one first and the other second, or you know, or you flipped them. I mean, oftentimes when you're talking about a high school plays, you know, that they do in the fall and the spring. In the fall, they'll try to do something that's kind of more of a holiday program, something that has to do with the holidays or winter or something like that. And then the spring one, they'll try to be more one that's lighter and more springy, summery kind of thing. So it does matter what order these are. So long story short, through my ramblings, it's a P. Okay, she's got 9 to pick from, and she's going to pick 2. Order matters, and so it's a 9P2. Comes out to be 72. And so what would be a situation where the order didn't matter? I think this is a bad example, but I'm going to show it just because you may run across one in your homework. I don't think this is very clear that this is supposed to be order not matters. It says an advertising exec must select 3 different photos for a flyer. If she has 10 to pick from, how many ways can she select? This could easily be confused because you're saying, oh, I'm setting up a flyer. Where I put those pictures in the flyer matters. But she's not picking where they go in the flyer. She's just selecting the 3 that are going to go in the flyer. and I guess she's going to send it to some art department or something. They're going to decide. But she's only selecting the 3. So she's just selecting the 3, forwarding them off to the art department. She's not picking the order. So in this case, that's just a C. So she's got 10, order does not matter, 3, and you could do it the hard way, 10 factorial over 7 factorial, 3 factorial, or you could just do 10C3, and again, like I said, they got stuck on the 120.
If you go back to the musical
Mhm.
example,
Mhm.
did it say 987?
Let me see. 987 factorial. So the 7 factorials would cancel.
Oh, okay.
Yeah.
Sorry, it's little. I didn't see it. My bad.
Yeah. So here, let me zoom it up a little bit. So yeah, it says 987 factorial, and so the 7 factorials cancel. So basically 987654321, and then on the bottom 7654321. But the 7654321 cancels with the 7654321. So all you have
Right.
left is the 9 and the 8. Yep. Okay.
Makes sense. Sorry about that.
That's okay. No, I know it gets, I don't know what devices you guys are trying to watch on and stuff. So this next one, I'm going to hold off on. I'm going to do something really quick. I want to talk about committees, because committees get confusing. If you're picking a committee and you just have representatives on the committee, does the order matter? So
No.
let's say you're thinking, you're right. Let's say you're just thinking about, okay, I need 2 people from this class to go represent us on the student council or whatnot. It doesn't matter whether you pick student D and then student F, or student F and then student D. Both of those people are going to go represent you on the committee in the same capacity. So if they're just representatives, the order doesn't matter. Okay? But if you're making a committee, and on that committee, you have a president, a vice president, a treasurer, and a secretary, does that matter? Does the order matter?
Yes.
Yes.
Absolutely. So in this case, if they're putting these in spots, the order matters. But if they're just going all in the same capacity, then the order doesn't matter. So they're both committee problems, but one, the order doesn't matter, and one, it does. Same thing with if you think about clothes. If you're just throwing clothes in a bag to take on a trip, does the order matter?
No.
No. But if you're selecting outfit, or if we don't even say outfits, just say certain days. So if you're deciding what shirt you're going to wear on Monday and what shirt you're going to wear on Tuesday and what shirt you're going to wear on Wednesday, does the order matter?
Yes.
Yes. So you can't say all committee problems are P's or C's, or all, picking clothing items are P's or C's. It depends on what you're doing with the things. So if you're actually deciding I'm going to wear my blue shirt, then my red shirt, then my yellow shirt, the order matters. But if you're just deciding I'm going to throw my blue, my red, my yellow shirt in my bag and take it on the trip, the order doesn't matter. So you have to kind of look at those different things, what's being done with it. If you're taking, this is an old-fashioned problem, but say you're taking CDs in your car for your trip. If you're just taking them in your car for your trip, order doesn't matter. If you're deciding what order to play them in, you're making some sort of a tape or something, and you're saying, I'm going to put this song, then this song, then this song, or this CD, then this CD, then this CD, the order matters. So you really have to look at what they're saying. Are they saying what goes into your, what songs go into your playlist, or what order the songs are going to get played from your playlist? Those are 2 different problems. One's a C, one's a P. So, okay, let's clear this up, and we'll do we only have 1 problem, and we're done for today. we're closer to the 3-hour mark than the 2.5-hour mark, but oh well.
I appreciate it anyway. Thank you.
Oh, no problem. I just sometimes I'm like, do I ramble too much or? All right. So on this next one, this is a little bit higher level problem. This is another one that is homework but not test. On the test, I'll just ask a straight P or C problem, probably one of each. So on the homework, this one's a little bit more complicated, okay? This one, we have a club where there's 7 women on the club and 5 men on the club. And they're gonna pick a committee to do something. But they're being very specific that on the committee, they want there to be 3 women on the committee and 2 men on the committee. When you see something like that where they're splitting it, I think in your homework you'll see one where it says you're going to have different professors go represent on the committee. Like you have this many physics professors and this many philosophy professors. Well, hopefully I don't do 2 Ps, but chemistry professors and math professors. And they're trying to, you know, make these committees, but you want a certain number of each type. When they start doing that, it gets a little bit more complicated. What you basically have to do is you have to think of it as I'm making a women's committee and I'm making a men's committee, and then I have to multiply the different possibilities to see the total number of ways for it to be done. So you have to separate it by the kinds that there are and then multiply those possibilities to get the overall possibilities. So in this case, since I have 7 women, I'm going to pick 3 of them. That's a 7-3. Does the order matter or not?
No.
No, because it just says a committee chosen. No presidents, vice presidents. They're not put in positions. It's just chosen. So, yep, 7, choose 3. For men, we have 5, and we're going to choose. Again, the order doesn't matter. We're going to choose 2. So we calculate those separately. So there's basically 35 ways to pick the women that are needed. There's 10 ways to pick the men that are needed if you calculate these out. And so you could take configuration 1 for the women with configuration 1 for the men, 1, 2, 1, 3, 1, 4, all the way up to 35 and 10. So you have 350 different ways, because you could have committee 1 for the women with committee 1 for the men, committee 1 with 2, committee 1 with 3. Well, this goes all the way down to 35, and then all the way up this way to 35, 10. So you have 35 ways for the women, 10 for the men, for a total of 350. Not a test question, but there is one, I think there's one of these on the homework. And the key is to split them up. Don't try to do, what people will try to do often is they'll try to add these together and do it as like a 12-5. They'll say 12, choose 5, because there's 12 total people and you're choosing 5. But that takes away from the fact that you have a very specific way you want to pick them. So you can't do that. All right. I think we're going to call it a day. If you guys have any questions on your homework, and I would very highly recommend you start chapter 4 early. It's one of the longer ones as far as the time it takes. So make sure you watch the 4 or 5 video and get started on that homework as soon as you can.
What's your estimate of how long 4 will take?
Oh gosh, I mean, that's really dependent on the person, but if I had to estimate, I would give yourself
Average.
at least a couple hours to do chapter 4 homework. At least a couple,
Okay.
if not more like 3 or 4, maybe an hour per section. Okay. So don't leave it till 5 o'clock Sunday night, or you'll be hating yourself. So, all right, everybody, have a great rest of the week. And like I said, don't feel like just because I'm not going to do the Zoom lectures anymore that I'm not here. Please let me know if you have a question. We can do a Zoom. We could do a group Zoom if several people have the same question, or I could do it with an individual, like an office hours kind of thing. I can answer a question in an email. I'm still here. I'm not going anywhere. So take care and have a great week.
Thank you.
Bye-bye. You're welcome. Thanks for being here.